So there are lots of multiverses, actually, in physics. One of them is called the inflationary multiverse, which is we have a theory of essentially what happened before the Big Bang.
Let's face it, to think that the universe has a history that started with a kind of birthday some 13.8 billion years ago is weird. The most popular theory of our universe's origin centers on a cosmic cataclysm unmatched in all of history, the Big Bang. In the first 10 to the power of negative 43 seconds of its existence, the universe was very hot, very dense, a single point in space that was less than a million billion billionth the size of a single atom. But in something like 1/100th of a billionth of a trillionth of a trillionth of a second, it underwent an incredible growth spurt. During this burst of expansion, which is known as inflation, the universe grew exponentially and doubled in size at least 90 times. After inflation, space continued to expand, but at a much slower rate, and eventually, we see the universe that we observe today. But if everything that happens can be attributed to a cause, what caused the universe? What came before the Big Bang? Until a few centuries ago, the answer was easy. Some eternal deity set everything in motion. Even Isaac Newton believed that God created the universe some 6,000 years ago. Later, many scientists, including young Albert Einstein, assumed the universe itself to be eternal and everlasting. But when cosmic expansion was discovered, a Belgian cosmologist and Jesuit priest, Georges Lemaitre, realized there must have been a beginning, a scientific version of Genesis, so to speak. But not that everyone immediately agreed. For instance, well into the 1960s, Fred Hoyle's steady-state theory was quite popular among iconoclastic scientists as well as laypeople. Hoyle accepted the expansion of the universe, but he didn't believe in the Big Bang. Instead, he believed that a slow, continuous creation of new matter could keep the average density and the general properties of the universe constant over time. Popular in the 1950s, steady-state theory claimed matter is continuously created as the universe expands, a theory overtaken by the Big Bang idea that density drops as galaxies move away from one another. However, the 1964 discovery of the cosmic microwave background was the major nail in the coffin of the steady-state theory. Ever since, supporting evidence for the Big Bang origin of our universe has accumulated to a point where there's hardly any doubt left. Still, no one has the final answer to the question, what happened before the Big Bang? Could there have been a universe before the Big Bang? Most scientists simply ignore the question, as it seems to be too hard a nut to crack. When astronomers talk about the Big Bang, they usually do not refer to the very beginning of the universe, but to the incredibly hot and compact state of the universe in the first couple of minutes of its existence. To some extent, this is because no one has a real clue about the true nature of time, let alone about the beginning of time. British physicist Julian Barber, for one, has argued that time doesn't even exist, except as an illusion in our minds. According to others, including Stephen Hawking, time came into existence together with the universe, rendering the whole concept of the word before meaningless. Asking what happened before the Big Bang would be like asking what lies north of the North Pole, or what distance is shorter than zero. That means, although effects within the universe have causes, the universe as a whole may not have or need one. Of course, such an answer doesn't feel very satisfying. In this dilemma, some famous physicists say that they can sketch out some possible scenarios.
So there are lots of multiverses, actually, in physics. One of them is called the inflationary multiverse, which is we have a theory of essentially what happened before the Big Bang.
Imagine that the universe we observe, from end to end, is just a drop in the cosmic ocean. That beyond what we can see, there's more space, more stars, more galaxies, and more everything, for perhaps countless billions of light years farther than we'll ever be able to access. and that as large as the unobservable universe is, that there are again innumerably more universes just like it, some larger and older, some smaller and younger, dotted throughout an even larger space-time. As rapidly and inevitably as these universes expand, the space-time containing them expands even more quickly, driving them apart from one another and ensuring that no two universes will ever meet. It sounds like a fantasy picture, the scientific idea of a multiverse. But if the science we accept today is correct, it's not only a valid idea, it's an unavoidable consequence of our fundamental laws. The idea of the multiverse has its roots in the physics required to describe the universe that we see and inhabit today. Everywhere we look in the sky, we see stars and galaxies, clustered together in a great cosmic web. But the farther away in space we look, the farther back in time we look as well. The more distant galaxies are younger, and hence less evolved. Their stars have fewer heavy elements in them. They appear smaller. As fewer mergers have happened, there are more spirals and fewer ellipticals, which take time to form from mergers, and so on. If we go all the way to the limits of what we can see, we find the very earliest stars in the universe, and then a region of darkness beyond that, where the only light is the leftover glow from the Big Bang. But the Big Bang itself, occurring everywhere at once some 13.8 billion years ago, wasn't the start of space and time, but rather the start of our observable universe. Before that, there was an epoch known as cosmic inflation, where space itself expanded exponentially, full of energy inherent to the fabric of space-time. Cosmic inflation is itself an example of a theory that came along and superseded the one that came before it, in that it was consistent with all the successes of the Big Bang and encompassed all of modern cosmology. It explained a number of problems that the Big Bang couldn't address, including why the universe was the same temperature everywhere, why it was so spatially flat, and why there were no leftover high-energy relics like magnetic monopoles. And it made many distinct new predictions that could be tested observationally, most of which have been confirmed. However, there's also one consequence that inflation predicts that we do not know whether we can confirm or not: the multiverse. The way inflation works is by causing space to expand at an exponential rate. This takes whatever existed before the hot Big Bang and made it much, much, much larger than it was previously. So far, so good. This explains how we get such a uniform, large universe. When inflation ends, that universe gets filled with matter and radiation, which is what we see as the hot Big Bang. But here's where it gets weird. In order for inflation to end, whatever quantum field is responsible for it has to roll from the high-energy, unstable state that drives inflation down into a low-energy, equilibrium state. That transition and rolling down into the valley is what causes inflation to come to an end and create the hot Big Bang. But whatever field is responsible for inflation, like all other fields that obey the laws of physics, must be an inherently quantum field in nature. Like all quantum fields, it's described by a wave function, with the probability of that wave spreading out over time. If the value of the field is rolling slowly enough down the hill, then the quantum spreading of the wave function will be faster than the roll, meaning that it's possible, even probable, for inflation to wind up farther away from ending and giving rise to a Big Bang as time goes on. Because space is expanding at an exponential rate during inflation, this means that exponentially more regions of space are being created as time goes on. In a few regions, inflation will come to an end, where the field rolls down into the valley. But in others, inflation will continue on, giving rise to more and more space surrounding each and every region where inflation ends. The rate of inflation is far more rapid than even the maximum rate of expansion of a matter and energy-filled universe, so in very short order, the inflating parts take over everything. According to the viable mechanisms that give us enough inflation to produce the universe we see, there are many more regions of space surrounding our own, where inflation did end. where inflation doesn't end right away. This is where the phenomenon known as eternal inflation comes from. Where inflation ends, we get a hot Big Bang and a universe, of which we can observe part of the one we're in, very much like our own. But where inflation doesn't end, that produces more inflating space, which gives rise to some regions that will have hot Big Bangs causally disconnected from our own, and other regions that will continue to inflate, and so on. This picture of huge universes, far bigger than the meager part that's observable to us, constantly being created across this exponentially inflating space, is what the multiverse is all about. It's important to recognize that the multiverse is not a scientific theory on its own. It makes no predictions for any observable phenomena that we can access from within our own pocket of existence. Rather, the multiverse is a theoretical prediction that comes out of the laws of physics as they're best understood today. It's perhaps even an inevitable consequence of those laws. If you have an inflationary universe governed by quantum physics, this is something you're pretty much destined to wind up with. It's possible that our understanding of the state before the hot Big Bang is incorrect, and that our ideas about inflation are completely wrong for this application. If that's the case, then the existence of a multiverse isn't a foregone conclusion, but the prediction of an eternally inflating state where an uncountably large number of pocket universes are continuously born and driven inextricably apart from one another is a direct consequence of our best current theories, if they're correct. So, what is the multiverse? It may go well beyond physics and be the first physically motivated metaphysics we've ever encountered. For the first time, we're understanding the limits of what our universe can teach us. There is information we need, but that we'll never obtain in order to elevate this into the realm of testable science. Until then, we can predict, but neither verify nor refute, the fact that our universe is just one small part of a far grander realm, the multiverse. While many things remain unknown, there are some way to get to somehow the multiverse. But to do that, we have to start with just the universe. By definition, the universe is all the things. It is the sum total of complete physical existence. If it's a thing, it's in the universe. But even with that definition, we can start to crack the door to other universes. One way to do that is to recognize that the universe is only so old, and light can only travel at a finite speed. So, there's a limit to what we can observe in the universe. That limit is about 45 billion light-years away. However, that explanation gives you a very weak vision of the multiverse. Actually, there's more to the universe than what we can observe, so there's more stuff out there, more stars, more galaxies, maybe even more intelligent creatures than we could ever make contact with. All of these things are in the universe, but are definitely not a part of our own world. In the multiverse, our universe is merely one of an infinite chain of universes. Imagine a giant foam like the top of a bubble bath. The multiverse is the foam itself, always growing and always creating new bubbles, with each bubble acting as its own independent cosmos. All of these bubble universes exist within the same framework of space-time. If you point your finger in any random direction, somewhere out there, past some unfathomably huge distance, is another universe, and beyond that, another, and beyond that, another. If this kind inflation truly never ends, then there are an infinite number of universes out there in the multiverse. Each one of those universes could have ended their local inflation in the same way, but it's also possible that as each universe pinched off, it got a brand new set of physics to go along with it, with different collections of forces and particles. Some of those universes would look incredibly similar to our own. Others may have failed, full of nothing but void. Some may be far stranger than we can possibly imagine, and some may be exact replicas of us. If, and this is a big if, there are only a finite number of ways to arrange all the particles in a given universe, then with an infinite number of universes, you're bound to get repeated copies. That means that not only is there another universe out in some random direction, but that if you follow that line far enough, you'll encounter a duplicate of you doing the exact same thing right now, in this present moment. This is all pretty wild but difficult to test. The problem is that all the bubbles of the multiverse are completely inaccessible from each other. They exist, but not in any connected way, so we can't just get in a rocket and fly off to head to our nearest neighbor. But there may have been some cosmic accidents in our ancient past. When our universe was younger, it had just broken off from the larger inflation-driven flow. If another bubble universe just happened to nucleate close to ours, then there's a small chance that our universes may have briefly intersected before being permanently driven away from each other. The chances of that happening are incredibly small, but not zero, which provides a way to test the multiverse. Unfortunately, no observations of the larger cosmos have revealed any indications that we have suffered such a collision. While those experiments don't rule out the multiverse idea, they don't exactly help. The only thing left we have to go on is our theoretical understanding of the early universe, which we don't really understand. We have only a vague picture of what inflation is like. We do not know what powered it, why it had the energies that it did, or why it shut off in our cosmos. We don't even know if inflation automatically leads to a multiverse, or if we're misunderstanding our own math. But while physicists continue to debate the idea, it does make for a good story. But put multiverse aside, we have some alternatives, one of which is known as the cyclic universe model, and it argues that our current observable universe is part of a series of universes. Our universe is currently expanding because of the Hubble parameter, and if that parameter stays constant, it will expand forever. But if the Hubble parameter is cyclic, then the universe will start contracting at some time in the future. It will contract until it reaches a new, hot, dense state, a new Big Bang for a new universe. A cyclic universe needs no beginning. It always was, always is, and always will be. But the model isn't without its problems. One of the main ones is the problem of entropy. Entropy is a measure of disorder in a system, and according to the laws of thermodynamics, can never decrease. In a simple cyclic universe model, the entropy of any given universe must be at least a little greater than its parent universe. So, if universes cycle to an infinite past, the current universe would have infinite entropy, which it doesn't. So there must have been some initial universe with low entropy, and we're back to the beginning. There is a way to get around this problem. The universe could have an overall scale factor. If that scale factor increases with each universe, then the entropy problem goes away. What's interesting is that this scale factor is conformally invariant. This means it doesn't change how the universe appears. Each universe might be twice as big as the previous one, but everything within that universe scales by the same factor. If you double the income of everyone on the planet, but also double the cost of everything, then nothing has really changed. This conformally invariant scale factor allowed the cyclic universe to exist without a beginning. Each universe has a cause, and it's turtles all the way down. But a new study has found a flaw in this idea. The team looked at the mathematical structure of cyclic universe models within general relativity and found that all of them are geodesically past incomplete. In other words, within the bounds of general relativity, you cannot trace a universe like ours back through an infinite cycle of universes. There may have been a vast number of universes before ours, but there must still have been a first universe. So the cyclic universe model can provide a cause for our universe, but it only kicks the problem of beginnings down the road. Even if our universe wasn't the first, some universe was. At least for the usual cyclic universe models. As the authors point out, their work doesn't apply to conformal cyclic cosmology proposed by Roger Penrose. In that model, the scale of each universe is infinitely larger than the cycle before. The authors plan to look at that model next. And thus begins a story for another time. Another approach involves M-theory, which is a unifying framework in theoretical physics that attempts to combine the various string theories and supergravity into a single, coherent theory. It is considered one of the most promising candidates for a theory of everything, which aims to describe all fundamental forces and particles in the universe within a single, all-encompassing framework. The M in M-theory has been interpreted in various ways, including membrane, magic, mystery, and matrix, reflecting its complex and somewhat enigmatic nature. M-theory has profound implications for cosmology, the study of the origin, evolution, and eventual fate of the universe. One of the most significant contributions is the idea of the multiverse. In M-theory, our universe could be one of many universes, each with its own distinct physical laws and constants. These universes might be connected through higher dimensional spaces and could interact in ways that might be observable, such as through gravitational waves or other cosmic phenomena. Another intriguing aspect of M-theory in cosmology is the concept of brane-world scenarios. In these models, our four-dimensional universe is viewed as a three-brane embedded in a higher dimensional space. This perspective can provide novel explanations for various cosmological observations, such as the nature of dark matter and dark energy, the hierarchy problem, and the initial conditions of the Big Bang. Despite its elegance and potential, M-theory is not yet fully understood, and many of its mathematical formulations and physical predictions remain speculative. One of the significant challenges is the lack of direct experimental evidence, as the energy scales at which M-theory's effects become apparent are far beyond the reach of current particle accelerators. Researchers continue to explore the mathematical structure of M-theory, develop new computational techniques, and search for indirect evidence through cosmological observations. Advances in technologies like gravitational wave detectors and space-based telescopes may eventually provide the necessary data to test M-theory's predictions. In summary, M-theory represents a bold and ambitious step toward a unified understanding of the fundamental nature of the universe. While it is still a work in progress, its potential to reconcile the different forces and particles within a single theoretical framework makes it a central focus of modern theoretical physics and cosmology. In the end, we have to admit we're ignorant about the true beginning of the universe. And even if we lean towards an eternal multiverse with no real beginning at all, we don't know why there is something or, more to the point, why there is everything instead of nothing. In other words, the universe is simply too complicated for humans to ever understand completely. That's all the information that we have for today. Don't forget to thumbs up if you enjoyed today's episode, subscribe if you haven't already, and be sure to hit the bell so you never miss out on future episodes. Your support motivates us to continue creating more and more quality videos. As always, thanks for watching, and we will see you next time.